speaker, Armando Fox.
Okay, thanks. I am Armando, and despite being a professor, I will try to be brief. When I got involved almost by accident with this new thing called MOOCs, one of the reasons I was excited is if you count both my instructor time as a professor as well as my instructor time as a TA in one form or another, I've had the privilege of teaching at 4 of the best engineering schools in the world. A colleague suggested that I say 3 of the best plus Stanford, but I have more plans. So what I realized is despite the nearly 20 years in that gig, the total number of students I had ever had a chance to teach or to help learn really is more accurate. Right? We think of teaching students as something we do to them, but it's actually learning. It's something they do with our help, ideally. The total number of students that I had ever taught was this minuscule fraction. Right? They were the best students going to the best schools, and God bless how hard they worked. But I was excited when the idea of MOOCs came along and that there was this, at least a potential, that some of what we were doing that was successful in those settings might be able to reach many more students. And really, ever since the MOOC phenomenon started, there's been this tension of rich despite scale and rich because of scale. So I want to tell you a couple of examples of what that means to me and why I think there's actually an exciting opportunity to mix some of the best of both worlds very much in some of the ways that John De Niro was just mentioning. I'm going to show a slide that looks a little technical. Don't be afraid. I don't want you to think that you have to be a computer scientist to understand this. Here's a very simple thing I want you to get out of this slide is that there's 3 examples of code. Those are 3 actual submissions from 3 actual students answering the same programming problem. And they all solve the same problem. They all produce the correct answer. But you'll notice that one of them on the left is 3 to 4 times the number of lines of code compared to the one on the right. And it turns out that these are qualities that you can measure. There is a sense of programming style and being idiomatic and concise and elegant. And a lot of that has traditionally been aesthetic. It's the kind of thing where a TA goes over each assignment and makes specific comments about, oh, you could reduce these 4 lines down to 1 line if you made better use of this programming idiom. Normally, that's a human-intensive task. And we have been investigating a way to help automate it. This is actually work that is currently supported by an IBM Research Faculty Award. The idea is that with a lot of students, you can imagine essentially constructing a big graph of all of their submissions to the same problem. And here's a subset of that actual graph. In that graph, every little node represents 1 student's assignment. And there is a connection between 2 students if their assignments are similar in structure, but one of them is stylistically a little bit better than the other. And if you're a programmer, you can come talk to me about all the ways that we compute that. If you're not, you don't need to worry about it. The important thing is that we can take, for any one of these students, let's blow up a little part of that graph, we can ask, what could this student have done to make their code a little better? Well, rather than having a TA look at it line by line, we try to find another student who actually did a little bit better, but whose submissions are similar enough that we can look at the difference and then give the first student a hint on what they might have done differently. And in fact, each one of those corresponds to a student submission. Now, to make this work, you need several hundred or a couple of thousand student submissions, more than we typically see in a campus classroom. But because we're offering the same materials to Berkeley students as we offer in my massive open online course, once we generate the graph from the students online, we can use the graph for the Berkeley students. And in fact, we're going to do that next semester in my campus course. A similar thing we can do if we have that many students is we can do a clustering so that the instructor can say, oh my gosh, I've got hundreds of submissions, but surely there aren't hundreds of different problem-solving approaches. In fact, for this assignment, there's really like 4 or 5 general approaches to solving it. And within each of those approaches, students have variations on how they implemented the approach. So we can apply some fairly well-known techniques from machine learning, like clustering and dimensionality reduction, to give the instructor very quickly, just hover over an orange dot and see a representative example of a particular group of students' problem-solving approach. So this is a way in which we can actually exploit the fact that many, many students are trying to do the work that we give them. Another example of this, this is work that I actually worked on with Bjorn and with Marty Hurst, another colleague of mine here at Cal. We were aware of a lot of literature saying that in a classroom setting, when you ask students to discuss problems in small groups, they will often learn from the discussion process even more than they learn from a TA's or a professor's instruction. And we thought, well, could we replicate that in a MOOC, in an online setting where the students are not in the same room and maybe not online at the same time? So we actually built a system to do that. And a few of the interesting results when we sort of trialed the system is we found that when students engage in these discussions in an online setting, like a chat room, they actually are more likely to get the right answer. That students who are offered a bonus, if they all get to the same right answer, actually do better as a group. They're more likely to change to the correct answer. They're having real discussions. They're not talking about the weather or about the upcoming election. And importantly, if a group of students is such that none of those students initially came up with the right answer before the discussion, we found that it was less likely that any of those students would eventually get to the right answer. Now, if you're an instructor, that last one is really important, because what that says is you should try to mix up the students who didn't get the right answer in the beginning. Try to mix them into groups where there was a little stronger performance before the discussion. Now, in a classroom setting, it's very hard to do that. But in an online setting, it turns out we can do more with the online version of this student discussion than you can do with a brick-and-mortar version, because you can shuffle groups around. You can instrument every word that they type. You can do simple natural language processing to figure out if the discussions are substantive. So this is an example of taking an idea that actually did come out of brick-and-mortar classrooms. In the intent to scale it up, we discovered that the technology-enabled version maybe is superior in some ways to the version that predated it. And ironically, even though we haven't really had a lot of traction deploying it in MOOCs, it is being used in large residential courses at one of the universities that we're collaborating with in Australia, and hopefully here too. So this is my way of saying that I think there's a potential for interesting research here that goes as follows. We deploy some interesting ideas, like the ones that I've shown, to our campus students. We debug the ideas, and we get them to the point where they're ready for prime time. Then we can deploy them in a MOOC where the number of students using the technology actually lets us get a data set that is interesting enough to do something with. And then we deploy that back into the classroom. So I think the line between online and campus is rapidly getting blurred. I think there's an opportunity to really get the best of both worlds here. And just to very briefly address the last bit, I said rich despite scale is also a challenge. If we think about what John said, what a large number of TAs and teaching assistants and tutors are involved in 61A, students don't need to have FaceTime one-on-one with the professor every time they have a question. If that was true, then classes like John's would never work. In fact, the TA model has been successful in part because you don't have to be a world-class field expert to answer the students' questions. You have to be a course expert. And in fact, I'm working with a company now called Mentiv that is actually trying to bring this exact model to online courses. Students who have taken these courses and done well and are willing to be paid for their time will have live, weekly online TA-like sessions. And that way, we hope to bring some of the success that we've had in the student teaching model into the online world. So I'll leave you with that, and I'll pass the mic. Thank you.
Great. And finally, Kathy Kim.